Hello everybody, this is Nicolas Zabaras. We continue our lectures on statistical computing and machine learning, and today will be our summary lecture on Bayesian linear regression. So we will see a few more prior models, how to do prediction with them, discuss some uninformative limits of conjugate priors, introduce what's called the Zellner G prior, and then maybe see some additional examples on model evidence, the way we apply it in empirical Bayes or evidence approximations in the earlier lecture. So the topics for today's lecture will include the following. We will consider the case when the variance in the likelihood model is unknown. So effectively our prior model will be a prior on both W, the regression coefficients, and the variance sigma square. We will introduce the Zellner's G prior and do the full Bayesian analysis and discuss also some uninformed limits of this prior that they are very common in practice. And then we will see a number of examples for this type of regression models and discuss the cases of computing the evidence so we can apply the evidence approximation. Finally, I'm going to close the lecture today with some brief discussion on the limitations of the type of models that we have seen where the basis functions are effectively selected regardless of what the data that we have to train the model are all about. So we a priori select a basis function, so we have to see what the limitation of doing that is about, and potentially of the techniques that you can hear in other machine learning courses on how to fix those limitations. Alright, so the goals for today's lecture will be to discuss regression models with priors on both W and sigma squared, to introduce the Zellner's G prior, use that to compute posterior marginals, the predictive distribution, evidence, as well as credible intervals. And in some sense, we will use these credible intervals to give one example of applying variable selection in our regression model. And then I'm going to give you a few more examples that you can play with both in the algebra and in computation that relate to the evidence approximation. Alright, so let's start with directly with our first example. So the first example will be a likelihood model that looks like this. This is our familiar likelihood model. So let me just remind you any change in the notation that we have here. The design metrics, I'm using capital X to denote that. My targets, instead of T that is used in Bishop's book, I'm using Y here. So this Y here is my training outputs. These are my training inputs. W are the parameters, and sigma square, we take it to be an unknown parameter. So the likelihood model after collecting n data points is written like that. Now usually when you write the design metrics as capital X instead of capital Phi, implies that you don't have any futures, you work directly on the inputs X, and that's why the design metrics that you see is denoted as capital X. Alright, so we're going to have to use a prior on both the regression parameters W and in the variance noise sigma square, and the proper prior to do this will be a normal inverse gamma. We already have seen this for as the conjugate prior for the mean and the variance for the case of the Gaussian distribution. We have done this example both for the univariate and the multivariate Gaussian distribution. So here is my conjugate prior, has parameters W0, V0, A0 and B0, and I'm writing it explicitly the way that you see it here. Just as a reminder here on my notation, D denotes the dimensionality of W, okay? So, and that includes the bias term as well. So D is the dimensionality of W. Okay, so if you multiply your likelihood and the prior that you see here, you get some normalized posterior that looks like this. So I have plugged in most of the terms that involve sigma square and W, so you get this rather complicated form. And obviously we anticipate that the posterior will be also a normal inverse gamma, and our problem will be to compute what Wn will be, what Vn, An, and Bn are going to be for this particular problem. I'm not going to do the algebra because it is literally identical to what we have seen for the Gaussian distribution, because we do have a Gaussian likelihood, right? The only difference is that W comes as parameters to define the mean of that Gaussian. That's the only difference. So if you go and you define Vn to be this, Wn to be that, An to be this, and Bn to be what you see here, okay? Then with some minimal algebra, it turns out that the posterior of W and sigma square, so this is the joint posterior of W and sigma square, is a normal inverse gamma, exactly in the same form as our prior, but with updated parameters that you see on the top. Now, as I have indicated in earlier lectures, when you have a joint posterior on W and sigma square, if you're going to report point estimates and uncertainties on the parameters of your problem, it only makes sense to actually use marginal posteriors. So it would be of interest to actually marginalize this joint distribution and figure out what the marginal of W is and what the marginal of sigma square is. Now, you can see here, if you marginalize on W, you can integrate this directly, this Gaussian, out, because there is no W on the second term. So obviously, the marginal of sigma squared will be this inverse gamma distribution, but unfortunately for sigma squared, if you try to produce the marginal of W, there is sigma squared coming here, and there is sigma squared coming there, so the algebra is a little bit more complicated, but it turns out that the marginal in W is a student t distribution with mean Wn, with variance, or this is approximately the variance given like that, and degrees of freedom 2 times An, where the parameters again have been defined in the equation on the top, and I'm writing you here the key elements of this student t distribution as a reminder. So just I'm summarizing the formulas for student t distribution with some of the moments. The expectation, the mean value is Wn. This is the covariance, is given by the degrees of freedom divided by the degrees of freedom minus 2 times lambda minus 1. Okay. So the mode is, as in the Gaussian case, is also equal in this particular case Wn. So you do have the marginal, you have everything, okay? And what remains to actually define is what the predictive distribution is going to be. So if we have some new input, we would like to know what is the corresponding output for that new input. So again, I will strongly recommend that you do the calculation in computing this marginal in W. If you need help, you can go back and look at the earlier lecture on how we did this type of calculation for the univariate Gaussian. Actually, I can tell you, and there is a hint on this slide, the only thing you will need to integrate sigma square out is actually to put that integral in a form that either gives you the normalization factor for a gamma distribution or the normalization factor for an inverse gamma distribution. And once you do that, you use the normalization factor, let's say, of the gamma distribution, immediately you will get the student t distribution. All right, so predictive distribution. This is not much different from what we have done before, but let me explain a little bit the notation. So I am doing the prediction at a whole new set of inputs, and I denote here with this matrix X curly. These are my test inputs expressed in the form of the design matrix. So this is the design matrix for my test inputs, and this Y bold curly is basically the corresponding outputs for those inputs. So again, what is the predictive distribution? Is nothing else but the likelihood, And you notice I am assuming here that I have m test inputs. That's how you get this m here, so that's my likelihood. And then I have effectively the posterior that we computed with these updated parameters wn, vn, alpha n, and bn that we saw before in the earlier slide. So to compute this distribution, obviously you have the difficult task integrating w and integrating sigma square. So you can guess that integrating w, it will require to close the square on w, because I see lots of quadratic terms. So that's algebra, okay? And effectively you can show, if you put these terms inside the exponentials together and you try to close the square, what actually you get this nice quadratic term that closes the square nicely. So when you integrate the exponential of minus of this, okay, divided by 2 sigma square, and then the sigma square to minus d over 2, okay, coming, you need this from the normalization of the Gaussian, the contribution coming from this first term will completely disappear, and what you're left is what you have in the last equation on this slide that you see here. So if you put all of this together and you call this whole thing as 2 beta, you're going to effectively having to do a computation in sigma squared. Now you're going to have to integrate sigma square out, or if you prefer to work with precision, you're going to have to integrate lambda out. And when you look, if you define, as I had on the previous slide, if you define whatever it is left on the exponential as 2 beta, and you define lambda to be 1 over sigma square, immediately what you get is the normalization factor of the gamma distribution, exactly as before. And immediately you can guess that the predictive distribution turns out to be a student t distribution. Okay, now this is this term that I had on the bottom of the earlier slide. That's that beta term that I define that comes. And then to put it in a student t distribution, there is a little bit more of algebra, because you still have to identify what the mean is, what the covariance is, right, and what the degrees of freedom are. And I have to tell you, as part of that algebra, you have to use the Woodbury formula for inversion. And in this particular case, you're going to have to use this form of the Woodbury formula. There is no assumptions really involved beyond the symmetry of V0, okay, and that is an obvious assumption in this problem. So the predicted distribution is a student t distribution with degrees of freedom 2an. We know the mean, we know the covariance, or approximately, the covariance. Again, you remember there is the degrees of freedom divided by nu minus 2 times this covariance. And there are 2 contributions, again, typical of this type of problems. One that has to do with the measurement noise, and another one that has to do with the uncertainties in W. And of course, it is this second term that you can guess that somehow it depends. So you're trying to do predictions of this test inputs x curly. So obviously this is the term where the distance of your training data contained inside Vn come together with the distance from the test data x curly. Okay, so the second term dictates basically how close the test input is to the training data, and depending on that, it gives you the corresponding variance. And as we expect, right, as we have seen, the error bars supposed to increase the further away we are from our training data points. Okay, so what we derived up now was a conjugate prior and the corresponding posterior for our regression problem. This was a prior of both W and sigma square. And now what I want to do is I want to consider some particular forms of this conjugate prior. So don't forget that everything we will say now comes from that conjugate prior. So this particular form is going to take A0 and B0 to be 0. Okay, it's going to take the mean in this Gaussian to be 0, and then we're going to make V0 to be some constant G times X transpose X inverse. And remember, X is your design matrix. So again, we see this paradox here that somehow we use a prior model on W and sigma square that involves the training data, but at least in this case, it is the training inputs that come to play a role, not the target values T. Okay, so this is what is called the Zellner's G prior. Okay, and in some ways, you can think of this G here playing the role of 1 over the regularization parameter that we have seen in ridge regression. Actually, that's not quite right, but you know, if X transpose X is the identity matrix, right? If you think X transpose X being the identity matrix, and we just have in here we have sigma squared times G, then G is indeed 1 over the regularization parameter that we have seen in ridge regression, because if you remember, the regularization parameter lambda in ridge regression was the precision of the prior divided by the precision of your likelihood, and in our problem, the precision of the prior will be 1 over sigma squared times G, all right? And the precision of my likelihood will be 1 over sigma squared. So the sigma squares cancel, and you can see that G plays the role of 1 over lambda. I'm only mentioning this, you know, so when you need to select a particular value of G in your problem, you can think 1 over G being analogous to the type of numbers that of the values that you are using when you select the regularization parameter lambda. All right, so in this particular selection of the parameters of A0 and B0, 0, and W0, 0, and V0 equal G, X transpose X inverse, this joint prior of W and sigma squared looks like this nice Gaussian times this inverse gamma. And what I'm going to do next is I am going to try to recognize some potential interesting aspects of this Zellner's G prior. Okay, so here is my Zellner's G prior. Now, if you select G to be equal to n, where n is the number of training data, so in essence, you can interpret this prior that you see on W and sigma square on this equation on the top. You can think of this representing what is called a uniform information prior. And what's the definition of a unit information prior? Is the prior that contains as much information as one data point. Now, why I'm saying that if G equal to n, this is equivalent to a unit information prior? Because we will see that if we take, a completely uninformed prior on W and sigma square, which is, you may remember from an earlier lecture that fully uninformed prior is 1 over sigma square. Okay, we will see this again shortly on the follow-up slide. So if you take a fully uninformed prior 1 over sigma square, it turns out that the posterior, its X transpose, the posterior precision, matrix is X transpose X. So you can see here that if G is equal to n, right? If G is equal to n, then the prior precision is 1 over n X transpose X, right? So again, this is the covariance. So the prior precision here will be 1 over n X transpose X, and the posterior precision is X transpose X. So you can see that with the choice of G equal to n, we're basically getting prior information that is equivalent to one data point. You can think actually of the posterior precision being n divided by n of x transpose x, and in the case of the prior we get a precision that's 1 over n x transpose x, so that corresponds to the precision of one data point. Okay, that's nothing significant, but this is a very popular prior, so the more you know, the better off you are. So let's see some uninformative limits of this G prior. Okay, so let's see what we can do, right? So before, you remember, we selected A0 equal to 0, B0 equal to 0, W0 equal to 0. So now what I'm going to do is I'm going to select V0 to be infinity times I, all right? And if you plug in this to your conjugate prior that we had before, effectively this leads to a joint prior on W and sigma squared that is of the form 1 over sigma to a power d plus 2. Okay, so this is an uninformative limit of the conjugate prior that we have seen before. So 1 over sigma to a power d plus 2. Okay, you can actually go a little bit further to discover this fully uninformative prior on W and sigma squared that we have seen in our lecture on prior models, which is 1 over sigma squared. And the way you can discover 1 over sigma squared from the conjugate priors that we consider here is actually with the following choice of parameters. You can take W0 to be 0, V to be infinity, and then you have to make the weird choice of A0 equal minus D over 2 and B0 equal to 0. And if you plug in all of this inside your conjugate prior, you do discover the 1 over sigma square joint prior of W and sigma squared that we have seen before. Okay? The idea here is when you see these priors being used in research papers or in books, I want you to remember that there are uninformative limits coming from a conjugate prior. All right, so they, you produce a conjugate prior, and then these are uninformative limits for this conjugate prior. Okay, now let me take this particular case of this joint prior of W and sigma squared being 1 over sigma squared. Okay, and what I'm going to do is I am going to write down the these parameters that we use for the posterior of our of our W and sigma square. So you remember we had computed these parameters Wn, Vn, An, Bn. So I want to write down how all these parameters look in the limits that I had before. All right, and those limits involve W0 equal to 0, V equal infinity, A0 equal minus D over 2, B0 equal to 0. So if I plug in this on my parameters for the for my posterior and my posterior marginals, what I get is I get simplifications because this matrix Vn becomes x transpose x inverse. You remember I mentioned before about this unit information prior that the prior that the posterior precision becomes x transpose x, right? This is from where this result comes. The mean of the my posterior turns out to actually be identical to the MLE estimate for W. You can see if this drops out and you substitute Vn to be x transpose x inverse, you actually do get the MLE estimate. An tends to be n minus d over 2 because A0 we selected it to be minus d over 2 to get this prior. And then Bn is simplified with some algebra that you will see at the bottom of the slide to s squared over 2, where s squared is this quadratic error between the my predictions using the MLE estimate for W and my target values Y. Okay, so that's what s squared is. And again, Wn is the same as my MLE estimate for W. So the only thing that you need to prove here is that this y transpose y minus wn transpose vn inverse wn is equal to this, and I do give you the derivation at the bottom of the slide. There is really just nothing else but expansion on the various terms and rearrangement, and you do get this final result, which is very appealing because again it tells you if you use the MLE estimate as parameters and you do predictions with that, it tells you what's the quadratic error in your training inputs. Now, what is interesting with this uninformative prior, this 1 over sigma square, is that you get this very nice marginal on W that is a student t distribution, and I've only substitute all the parameters we had in the expressions given earlier. I substitute all of them in terms of the specifics that we have for this uninformative prior, and we get this nice student t distribution with degrees of freedom n minus d. And it turns out, right, if you look at the the marginal of a specific parameter wj, that also follows this student t distribution. This metric c, by the way, there was no need actually to have a new matrix, but c here is nothing else but x transpose x inverse, okay? All right, so it turns out that the marginal of wj is given by this student t distribution, and what is surprising and actually an important result, this distribution turns out, for those who are familiar with frequency statistics, to be actually the same, or of the same form if you like, with the sampling distribution of the MLE. Okay, so effectively we get exactly the same result from a Bayesian perspective as we get from a frequency perspective, which means effectively that when you compute error bars or confidence intervals on Wj in the Bayesian way, those confidence intervals turn out to be the same as the credible intervals that you get, so these credible intervals that you get in the Bayesian setting, they turn out to be the same as the confidence intervals that you're familiar maybe with in the frequency setting. Okay, so one way or another, the results that frequencies reports as error bars on the parameters turn out to be the same that you would get with credible intervals in this fully Bayesian setting, using this particular uninformed limit of the conjugate prior that we introduced in the lecture today. All right, so actually let me do the following thing. Let me use these results to compute for this data set, the Caterpillar data set. This comes from the Bayesian core chapter on regression models. If you remember, because lots of you worked on this in the homework, you have 11 variables W. So what I am plotting here is I am plotting the mean of the posterior of each of these coefficients, and this is the mean of the marginal posterior of these coefficients, and then I am plotting also the standard deviation and this 95% confidence interval. Okay, now you notice I mark some of these coefficients in red, and next to it I put a star, and the idea here is that these W's that have a star next to them are W's that they are important when it comes to the predictive ability of the model. And what I mean with that, there are W's that you need to have in your model to do correctly the predictions. And the reason I say this is because if you look at any of these intervals, you'll notice it does not contain the value 0. Okay, so this is all positive, this is all negative, this is all negative, and all positive. And you can think of this marginal on posterior on W being a Gaussian distribution, so it has lots of probability mass in its mean, so if the mean is negative or it's very positive, if it doesn't contain the zero. If the mean is not close to zero, then you can say with confidence that these W's are not going to turn out to be zero, so you do need them in your model. So effectively, you can think using these confidence intervals and this nice trick, checking if the zero value belongs in your 95% credible interval. You can use this trick to figure out which variables stay in your model and which variables actually can be removed without degrading the predictive capacity of the model. So this is what we call variable selection. Right, so I mean, I call it variable selection. Somebody can still call it a model selection because which variables you keep in or out in your model, it's still part of your model. But in essence, the way that I prefer to look at it is you decide, you look, for example, if these W's correspond, and they do in this particular case, to different input directions, right, or input dimensions, you can immediately see that the direction 3, 6, 7, 8, 9, and 10 can be removed, and they don't really affect the predictive capacity of your model. Now, before I finish with this example, right, let me just say that you can get exactly the same results in the frequency setting using p-values at the 5% level. We already, expect this because this marginal on Wj that we got is the same as the sampling distribution of the MLE, okay? But let me just close by saying something that I think we often, at least frequently statisticians don't often tell you about this. This MLE doesn't exist if the number of data points is less than the dimension d of your problem, okay? So if n is less than d, effectively the MLE doesn't even exist. But the Bayesian inference that we did here works very well, assuming that you use a proper prior, and it doesn't depend if n is less than d or n is greater than d, etc., because as we have seen and discussed in earlier slides, in the Bayesian setting, you are effectively integrating the parameters out, and the Bayesian setting defines for the data set an effective number of parameters that can be defined from the data, and the rest basically are being controlled by the prior model. All right, let me keep moving, and I'm going to do another example that practically looks the same as what we already have seen, but it's a little bit, the notation a little bit more general, so I'm going to try to go fast. So here is a prior. I am working now with precision beta. Before we had sigma square. So you anticipate basically here that in my prior, instead of having a normal inverse gamma, I am going to have a normal gamma distribution, and here it is, all right? So the notation is not very much different from what we had before. And, you can show that the posterior of W and beta is given by also a normal gamma distribution. And, how do you actually solve this? Again, I strongly advise you to go through the algebra. You multiply the likelihood for n data points. You multiply with your prior model. Remember, W is, I take it here to be of dimension m. I apologize for changing the notation from d to m, but sometimes it's better to stick with the notation of the original reference to avoid typing mistakes. So hopefully from the context of the slides you can understand that m is the dimension of w. So that's the posterior, and literally what you need to do is you just need to recognize from it a Gaussian for w, so it means you have to close a square on w, and then hopefully what is left out, you have to recognize it as a gamma distribution, and this is what you get, and these are the parameters for this posterior. Now, you can use this posterior compute a predictive distribution. So the predictive distribution shown here is at, so if you already have, I don't have on this slide the predictive distribution, my apologies. This is more interesting. What we have on this slide is the computation of the model evidence, okay? And you remember the model evidence is really what we need to do model selection. And the model evidence is nothing else but the likelihood, right, of my training data times the prior on W given the precision beta times the prior on beta, and then we have to integrate W and beta out. And the remaining of the equations that you see on this slide, there's nothing else but substituting what the likelihood is, what the prior W given beta is, and this gamma prior on the precision beta. So what you will need to do is, right, you're going to need to integrate W out. So that's immediately tells you need to close the square so you can get the normalization factor of a Gaussian in W. And the only thing I will pay your attention is to be careful, right, if you're going to close the square on W, you have to remember that W has, it's of dimension M, all right? So it's of dimension M, so close the square, but account for that properly. And then you're going to get something that involves only beta, and maybe that integration that you have in beta hopefully will be the normalization factor of a gamma distribution or an inverse gamma distribution, depending on how you decide to perform the integration in beta or in maybe 1 over beta, the way we did earlier in the lecture today. Okay, so I'm not going to go through the details. Basically, I described to you get rid W by integrating it out, by closing the square. Then what is left is the normalization of a gamma, cut and paste formulas for the normalization of the gamma with the correct parameters, and there is a very nice expression that you see on the bottom for the this marginal likelihood for this model, where again we use conjugate priors to do the analysis. So if you have hyperparameters in your model that you need to select, or even if you want to select the order, let's say, of your polynomials that you use in regression, you can use this marginal likelihood to try to maximize it and do this evidence approximation or empirical Bayes that we have seen in our earlier lectures. Okay, let me go through the last example, right? And I'm doing a lot of the examples so that you can see that the algebra, at the end of the day, it does look the same, even if you change a little bit your prior models here and there. So what I have is a likelihood model written like that. So phi is my design matrix that I'm going to show to you for the particular example I have in mind. We're going to use a conjugate prior, so W given sigma squared will be a Gaussian, okay? The sigma squared, the prior, is going to be an inverse gamma, exactly as before. And instead of using the G prior that I had before, what I'm going to take for this matrix M to be I divided by C. And let me just give you the particular form of the design matrix, right? So the design matrix in every row for every data point, so this is for data point 1, I have this powers 1, x1, x1 squared, x1 m. So the degrees of freedom in my problem, so the number of variables W that I have in my problem are m plus 1, okay? So the number of variables are m plus 1. This is a mistake here, I need to correct it in the posted slide. This little k should be capital M. So remember, the total number of W's that I have is m plus 1. For an mth order polynomial, accounting for the bias term, W0. Okay, so this I matrix here, all right, coming in the prior of W, is a matrix of m plus 1 times m plus 1. So this looks like the G prior. The only difference, I don't have this X transpose X here. I have this identity matrix just to make the algebra simpler. So what you can do is you can write your likelihood model the way we know how to do it for n data points, nothing fancy. Here is the likelihood model. What I have done is I have done a little bit of rearrangement of the likelihood using an identity that we have seen in multiple times before. So if you bring in the MLE estimate for W that is here, all right, you can simplify this term inside the exponential using S squared, and then this quadratic term that is W minus the MLE estimate. Okay. So what is S squared is what we have seen before, is the error my model does when I plug in the MLE estimate for the parameters, and so that's the error from the target training data Y. All right, so that's what the S squared that we have seen in earlier slides. And again, this is a standard sort of calculation that you need to do to bring the MLE and simplify this equation in this form. Now notice S squared here, there is no W dependence, and the nice thing here is I have this quadratic term that involves W minus W MLE. Okay, so this is this is my likelihood model. All right, don't confuse this with a posterior. You can see a script L, and I'm writing like that to emphasize that this is a function of W and sigma squared. So when you multiply this with your prior models on W given sigma squared and on sigma squared, these are the prior models introduced 2 slides ago. This is what you get, and the only thing that I have done except multiplying by the prior, I expanded the quadratic term that I had before in here. All right, so I expanded this term explicitly, and this is what I have. Okay, so that's my the posterior, and now actually what I'm going to do is I intentionally do not give you in closed form the parameters for, so this posterior is going to turn out to be a normal gamma, inverse gamma distribution. So I don't give you the parameters for that distribution. So I want you to actually take the time and derive on your own those parameters. What I will need to use on the rest of this example will be this normalized form that you see on the top. But you guys maybe can do the algebra and produce what exactly the form is for this joint posterior. So what I want to do is I want to produce the evidence. Okay, the evidence will require this marginalization of this likelihood times the prior. So basically, so this is what I have here, right? I have the likelihood times the prior. So to get the evidence, that's the denominator in my posterior distribution W and sigma square, I will need to integrate the likelihood times the prior, and I will need to do this integration on W and on sigma square. Now the reason I expanded the W, that quadratic term in my likelihood that we saw in the previous slide, is because I need to combine those W terms from the likelihood with the W terms from the prior model, because if you're going to integrate on W, you're going to have to close the square. You're going to have to close the square on W, and then hopefully if you do that successfully, you will eventually need to perform the integration in sigma square. And actually looking at this slide, I notice the calculation proceeds the other way around from what I just described. I see first by calling this whole thing A, so I keep this because the function of W only. I keep it constant, and I do the integration on sigma square, and you can see the integration in sigma squared can be performed because it turns out to be a normalization factor for an inverse gamma distribution, right? So if I look, where is it, right? So if you look what it says inside, if I call this whole thing A, basically I have an exponential, right, of something over 1 over sigma squared, and then I have sigma squared to some exponent, and you can see immediately this is an integral that will give you the normalization factor of the inverse gamma distribution. So if you plug in this normalization factor, this gamma distribution coming from here divided by beta to a power, all of this defined by the particulars of that you see inside the integration here, you get a nice expression that depends only on A and has to be integrated in W. So this is this equation that involves only W, and now you're going to have to do the integration in W. Now it turns out that if you look very carefully and you do a little bit of an algebra, the thing that you need to integrate, it reminds you very, very much a normalization factor of a student t distribution. So without going through the details here, because it will take us 4 hours, if you define mu to be this nice thing here, where WMLE is my MLE estimate, so if you define mu to be like that, you close the square on W nicely like this with this covariance matrix that you see here, and then the remaining term is constant, it doesn't depend on W, so you can cut and paste the normalization factor then for a student t distribution corresponding to this, and at the end of the day, using the normalization factor for the student t distribution and a little bit of algebra, and using the definition of my MLE estimate for W and S square and mu that I just gave you, what you do get, you get this final result that in a very nice form gives you the evidence, it gives you the marginal likelihood, okay? And you can see that obviously depends on the training data, that's where capital Phi and Y come from. It also depends on these parameters A, and B, and C that we had in our prior model. So A and B were in the prior on sigma squared. C was a parameter coming in the prior of W given sigma squared. So we have all of these prior parameters. So actually what you can do is you can use this and optimize it. You can optimize it with respect to the hyperparameters and do evidence approximation to compute these optimal parameters in your prior model. Or you can even, if you decide to fix those parameters, you can optimize this with respect to the order of the polynomial that you use in your model. And this is exactly what I'm going to show you in this example. So what you see here is a particular data set, okay, and it's not very many points, it's less than 10 points. You can see fitting this with different orders of polynomials. Visually you can see that the quadratic term does very well, the cubic does very well, etc. But when you look at the model evidence, you can see that it's maximized for quadratic polynomials. So effectively the optimal order of polynomials, so the optimal complexity of your model is quadratic, m equal to 2, okay? So that's a nice way to use the model evidence, and remember it took us, and it will take you some algebra to derive this closed form, but when it comes to actually programming this closed form to compute the model evidence that you see on the right of the slide, that's literally one line of your code. Okay, so if you can do the calculation analytically. It only takes one line to program this. All right, so that's a very nice example. Another application on coming up with the evidence, an approximation for the evidence for our regression model, and then being able to use that to select the optimal capacity of the model, or to select these the hyperparameters in our prior model, the way we saw and discussed in an earlier lecture. Okay, so we're almost done. So let me just try to, since this is our last discussion on regression models for a little while, let me just say something about the limitations of the models that we have used. So if everything we have done, we have used basis functions, right? Obviously, we talked about the equivalent form of our model with this using kernels, where these kernels are defined from basis functions. Okay, we didn't generalize beyond that. It was an equivalent form. It was using kernels coming from basis functions. But generally, everything we have done, we have used basis functions that have been selected a priori. So we do not look at the data and say, this is how the data looks like, so let me select these basis functions because they may be better or worse. So we have not really put any thought on what basis functions we're going to use. Now, if you have a problem that has high dimensionality, you remember from the lecture on the Cursor dimensionality, the number of basis functions that you use is going to go to increase exponentially with the dimensionality of the problem. So that's already very bad news. You will not be able basically to use all the basis functions that you want. So if you try to have 5 dimensions and you try to use a polynomial of order 3 and you try to account for all all terms of order 3 in 5 dimensions, basically you will get thousands of W terms, and that is prohibiting for practical regression analysis. So what do we need to do in practice? And obviously we're not going to give you solutions to these problems, but one of the things we have not done up to now is we have not accounted for the fact that in all practical applications, these input training points xn that I gave you, even though they appear to be in vectors in high dimensions, in reality these training data points live in a very low dimensional manifold, mainly as a result of the correlations between the different input variables. So somehow it would be nice if we can account for this fact in the way we defined our basis functions. So in essence, we emphasized in an earlier lecture that it will make sense to use localized basis functions, and in that case, if you use localized basis functions, it will only make sense that these basis functions are scattered in part of your input space where you have data, all right, so near your data manifold if you like. So that's a very important considerations that you need to do this. So are there any methods out there that somehow can account for issues like that? Well, the answer is yes, and you may already know with the rise of deep learning and neural networks, you can do regression modeling with neural networks and deep learning. And, neural networks give you the ability basically to adapt the weights in the network in such a way that the basis functions that they produce vary only in regions of the input space that corresponds to the data manifold. So the problem that I mentioned before, in essence, is taken care. And actually, even more than that, right? We do not talk about the target values y or t, okay? And so if you have a high dimensional problem, is your output actually does your output depend on all the input dimensions? We already saw in the caterpillar example that only some of the input dimensions are relevant to the predictions of the model. So the idea here is, can we actually explore and find out for a given data set which directions of the input space the basis functions that are being produced need to respond to. And again, neural networks allows you to do this, right? So these are basically ideas that go with the general name adaptive basis functions, and neural networks is one of the methods that can be used to produce adaptive basis functions. But if you take an advanced machine learning course, you will learn that there are many more methods that actually they try in one way or another to address this particular problem. All right, so let me just finish here for regression models, and we are ready to start our discussions on the next lecture with Monte Carlo methods. So we will go away from having to do analytical calculations the way that we have seen in these lectures with computing analytically the evidence and the predictive distribution, the posterior, and effectively what we will try to do is we will try to develop methods that work with samples. All right, so this is what Monte Carlo method will all be about. Okay, so let me stop here, and we will see each other in 2 days. Bye.